Yeah. Now let us look into Taylor's theorem. So Taylor's theorem says if f is mapping from a comma b to r such that it should satisfy the first condition, that is f power n minus 1 is continuous on closed interval a comma b. And the second condition is f power n minus 1 is derivable, it is derivable on open interval a comma b. And the third condition is p belongs to a positive integer z plus, then like whenever if p belongs to a positive integer, then there exists some c belongs to a comma b such that this is a big formula, f of b is equals to f of a plus b minus a into f dash of a plus b minus a whole square by 2 factorial into f double dash of a plus so on up to the last one will be b minus a whole power n minus 1 by n minus 1 factorial into f power n of a plus Rn. Here Rn is equals to b minus a whole power p into b minus c whole power n minus p by n minus 1 factorial into p. This is f power n of c. This is the statement of Taylor's theorem. Now let us look into the proof of this theorem. The proof. So let us define, even here we are going to define a function phi. Let us define a function phi which is mapping from a comma b to r such that phi of x, I am defining this phi as phi of x is equals to f of x plus b minus x into f dash of x plus b minus x whole square by 2 factorial into f double dash of x plus so on up to b minus x whole power n minus 1 by n minus 1 factorial into f power n minus 1 of x plus some constant k into b minus x whole power p. So I'm just defining this phi of x like this. Now let us choose where this k, what is k? K belongs to some real number r. Okay. After taking k belongs to some real number r, now choose phi of a is equals to phi of b. This phi of a is equals to phi of b. And we know that, what is that we know? This f of x, f dash of x, f double dash of x and so on up to f power n minus 1 of x. What are they? They are all continuous functions. So f of x, f dash of x, so on up to f power n minus 1 of x are continuous on closed interval a comma b. Now where are these all f of x, f dash of x, f double dash of x and f power n minus 1? They are in phi of x. So from this we can conclude that phi of x is a continuous function. So phi of x is clearly a continuous on a comma b. As this is continuous, and what is this f dash, f double dash and all? They are derivables. So we can conclude this phi of x is derivable on open interval a comma b, as it is continuous and it is derivable. So what is the third condition of Rolle's theorem? That is phi satisfies all the conditions of Rolle's theorem. If all these three conditions are satisfied, like what is the third condition? This one, phi of a equals to phi of b. The first one is phi of x is continuous, phi of x is derivable, and phi of a equals to phi of b. So as all these three conditions are from Rolle's theorem, there exists a C belongs to AB such that, what is that? Phi dash of x C is equals to 0. Let this be equation 2 and let this be equation 1. Am I clear? As these three conditions satisfies, we can tell that there exists a C belongs to AB such that phi dash of C equals to 0. Now we have to differentiate this with respect to x. So what is that we'll get? If we differentiate with respect to x, phi dash of x is equals to, you'll have f dash of x plus b minus x into f double dash of x plus b minus x whole square by 2 factorial into f triple dash of x, and so on up to, one second, this will be, we'll just differentiate this again. What is the equation 1? Phi of x is equals to f of x plus b minus x into f dash of x, b minus x into f dash of x, plus so on up to b minus x whole power n minus 1 by n minus 1 factorial into f power n minus 1 of x. Plus we have k term, that is k into b minus x power p. We have to this was equation 1. So we have to differentiate equation 1, differentiating equation 1 with respect to x. So what is that you'll have? This will be phi dash of x is equals to, this will be f dash of x. Now this will become u into v. So how will you write that? B minus x into f double dash of x plus minus f dash of x into, this will become 1, this will be equals to 0. So this is the second term. Okay, am I clear with this? This, if you differentiate with respect to x, this will become 1 and this will be equals to 0. That is the reason we got minus f dash of x. And what will be the second term? Second term will also be u into v. And moving on to the last but one term, that is this one. So what is that will be? B minus x whole power n minus 1 by n minus 1 factorial into f power n of x. Why did we get n? See here, when you have f dash, you got f double dash. If you have n minus 1, you'll have n minus 1 plus 1. Minus 1 plus 1 gets cancelled, so you'll have n. So you'll do with respect to the nth term. So b minus x whole power n minus 1 by n minus 1 factorial into f power n of x minus, again you have to differentiate v into u, f power n minus 1 of x into x minus 1. You have to differentiate this one, this term now. So what will that be? That will be n minus 1 into b, this will be b minus x into n minus 2. Okay, and you can take by n minus 1 factorial. I hope I'm clear. I'm telling this again. This we have to do u into v. So u into v dash is f power n. Again v into u dash, f power n minus 1 of x into, this is in the form of d by dx of x power n. So you have to write n into x power n minus 1. So that is what we wrote over here. Okay. Now moving on to the next step. Minus this, again this last term is there now. So plus x k into p of b minus x into minus 1 with respect to x. So this you can write it as minus of k into p b minus x whole power p minus 1. Okay, there is the second step. Now moving on to the next step, that is phi dash of x. Phi dash of x is equals to 1 by n minus 1. See, now everyone look here, f dash of x gets cancelled. In the same way, this second term also will get cancelled. So this f bar n minus 1 term also will be cancelled, because here like the first term and the third term gets cancelled. In the same way, b minus x terms also gets cancelled. So the only terms which will be remaining is this and this one. So 1 by n minus 1 factorial into b minus x whole power n minus 1 into f power n of x minus k into b minus x whole power p minus 1. Okay, this is what will be remaining after these terms get cancelled. In the next step, from 2, what is 2? From 2, what is 2? One second. What is equation 2? Equation 2 is this. Phi dash of c is equals to 0. So from this equation 2, what is that we can conclude? Yeah, from 2, we can conclude that this phi dash of c is equals to 0. So we can make this right hand side equals to 0. So 1 by n minus 1 factorial into b minus x whole power n minus 1 f power n of x minus k into p into b minus x whole power p minus 1 is equals to 0. So from here we have to find kp, like move kp to the right hand side, you'll have kp into b minus x whole power p minus 1 is equals to this will be as it is. What is that? 1 by 1 by 1 by n minus 1 factorial into 1 by n minus 1 factorial into b minus x whole power n minus 1 into f power n of x. Okay, this is what we got, kp into b minus, oh sorry, yeah, we have to do with respective to c. So instead of x you write c, instead of x you just write c. Why are we writing c? Because what is equation 2? Phi dash of c equals to 0. In place of x we got to keep c. Okay, am I clear till here? Now moving on to the next step. In the next step, we just have to find k. So what will the k be? So k is equals to b minus c whole power n minus 1 minus p plus 1 by n minus 1 factorial into p into f power n of c. This is equation 3. If we find k, then this is what we'll get. In the next step, you got to take the value of phi of a is equals to phi of b. Now using this, we'll just get the entire solution. So what is phi of a equals to phi of b? What is phi of a? From the equation 1, f of x, f of x b minus a into f of f dash of x and all. So you got to write that with respective to a. So what is that? You'll have f of a plus b minus a into f dash of a plus b minus a whole square by 2 factorial into f double dash of a, and so on up to b minus a whole power n minus 1 by n minus 1 factorial into f power n minus 1 of a plus k into b minus a whole power p. That is equals to phi of b is, right, I'm just writing that as f of b. Okay, now from 3 and 4, this is 3 and this is 4. So what is that? You have to substitute the value of k over here. So the entire term, like till here, you got to write the same thing. I'm just writing this step. So what will that be? Instead of k, I'm just substituting that value. So if you substitute the value, what will that be? Plus you have to write this entire thing. b minus c whole power n minus 1 minus p plus 1 minus p plus 1 by n minus 1 factorial into p into b minus a whole power p is equals to f of b. So now this one minus 1 and plus 1 gets cancelled. So what is that you have? N minus p. I'll just rub this and write it again. So what is the term you'll have? After substitution, you'll just have b minus a whole power p into b minus c whole power n minus p by n minus 1 factorial into p into f power n of c. Okay, and what is that we have defined at the end? This is what is Rn. This is what is capital Rn. Okay, so b minus a whole power p, b minus c whole power n minus p by n minus 1 factorial into p into f power n of c equals to that is Rn. So the entire term, this everything will be equals to same thing. So you got to write that one, f of a plus b minus a into f dash of a plus b square minus a whole square by 2 factorial into f double dash of a and plus so on. The entire term is equals to f of b. Okay, so what is that we got? F of b is equals to f of a plus b minus a into f dash of a plus b minus a whole square by 2 factorial into f double dash of a, and this is the last term, that is Rn. Am I clear? The last but one term will be this one, b minus a power n minus 1. This will be the last term. Hence proved. Hence proved. Okay, I will just give you the quick summary of this. See, this is what the Taylor's theorem statement, that is f power n minus 1 is continuous, f power n minus 1 is derivable, and there exists c belongs to AB. See, whenever p is a positive integer, then there exists a c. So f of b is defined like this. Next, we have to just define the function phi. We have to first define function phi, and then we'll take the derivative of it. After all the cancellations, this is what we'll have, f dash of x. And then you'll have this one. You got to substitute k value. After substituting k value, what is that you'll get? There exists something. This is the starting of the proof, and then yeah, this is what the ending. This is the ending of the theorem. So this is what the Taylor's theorem says. Am I clear till here?